and do integration by parts with a twist. I notice that we have a product of functions here, and each of those functions has cyclic derivatives and integrals. The derivative of an exponential is an exponential. The integral of an exponential is an exponential. And similarly with sine or cosine, if you take multiple derivatives and integrals, there's a cyclic pattern to them. And that's kind of a hallmark of integration by parts with a twist. And when we do need integration by parts with a twist, it doesn't matter which function you put with u and which function you put with dv. So I'm going to do that. And when we take our derivative here, we will get that du is 3e to the 3x dx. And v, when we integrate, using the reverse chain rule, we will get sine 2x divided by 2. We're going to call this integral omega, and omega is going to then be equal to u times v, which is 1/2 e to the 3x sine of 2x, minus the integral of v du. v du is the bottom row here, and so we will have 3/2 e to the 3x times sine of 2x dx. And what we notice here is that we need to use integration by, and when we use integration by parts, again, we want to be consistent. We want to stick with the exponential with u and the trig function with dv. Now I'm going to make one little modification here. I'm going to move that minus sign in here, making that a plus. And that's just going to make my algebra a little bit easier in the long run. It's going to allow me to not have to deal with distribution of constants later. So I will choose for u the exponential and choose for dv the trig part. The derivative here will be minus 9/2 e to the 3x times dx. And the integral here will be minus cosine 2x over 2. So when we do our integration by parts this second time, that front term comes on down. And then we're going to have u times v. u times v is going to be positive 3/4 e to the 3x cosine 2x. uv minus the integral of v du. Well, v du is the bottom row here, and a negative times a negative is a positive. We multiply them together, we're going to get 9/4 e to the 3x cosine 2x dx. All right. And here's where the twist should be acknowledged. What we should be seeing is that that new integral is going to be identical to the original integral, except that there's a coefficient of 9/4. So that 9/4 can factor out to the front, and then we have e to the 3x cosine 2x inside the integral, which is what we called omega originally. So now we have omega on the left and omega on the right, and we can combine like terms. For the omega on the left, I will make it so that it has a coefficient that has a denominator of 4, so that we can add these together easily. When we add those together, we have 4/4 and 9/4. Adding is going to be 13/4 times omega. And that is going to equal all this stuff, which I'll write out this time. And as soon as we do that, as soon as we add that omega term to the left-hand side, we need to introduce a constant of integration here. Omega is representing an indefinite integral. All indefinite integrals have plus c at the end. And so as soon as we move this omega right here to the other side, we need to ensure that we have a constant of integration on the right-hand side. So that's when we introduce that constant of integration. And now we just need to multiply by 4/13. If we multiply the left side by 4/13, we will have 3/4 times 4/13, which will be 1. And over here, when we multiply by 4/13, we'll end up with 2/13 because there will be a cancellation with the 2. And when we multiply this by 4/13, we're going to end up with the 4's canceling, so we'll get 3/13 e to 3x plus, times, that should be a multiplication, times cosine of 2x plus c. And that is our final answer.